Dr. P. Nagaraj. He is currently working as Assistant Professor in the Department of Chemistry, Anna University, Chennai. Earlier, he worked as a scientist in charge at Spices Board of India for 5 years in research and development and also in quality control laboratory. He has finished his PhD in organic chemistry at IIT Delhi. He has also done his MSc Chemical Science at Pondicherry Central University. He has published 6 papers in international journal and also participated several international events in India and abroad. He has attended several conferences and delivered lecture as keynote speaker and also undergone 12 training programs. His area of research interests are isolation, synthesis of natural products and evaluation of their biological activities, carbohydrate-based natural product synthesis, enzyme catalyst organic synthesis, green chemistry, medicinal aspects of spices and spice products.
Welcome to UGC lecture series in Polymer Science. Today in this lecture we are going to study elastomeric material, some of the elastomer and its isolation properties, all these things we are going to study. Content of today's lecture is introduction about elastomers, elastomeric materials, synthetic polyisoprenes, silicones and siloxanes, butadiene rubber, thermoelastic butadienes. These are all the content we are going to study in this lecture. First of all, what is elastomeric material? Elastomeric material, it should have some common characteristics like large elastic elongations, that means almost double the elongation should be there, can be stretched and when immediately returned to their original length when the load was released. That is the peculiar property or characteristics of elastomer. Whenever you apply stress, it have to get elongation. If you release the stress, it have to come back to original position. And these are two important characteristic points for elastomeric material. And some of the other important points related to elastomeric materials are elastomers, sometimes called rubber or rubbery material. The term elastomer is often used interchangeably with the term rubber. So, rubber material also can be called as elastomeric material, and elastomeric material you can exchange the name like rubber material. Elastomers are usually thermosets, but may also be thermoplastics. So, both the case elastomers can be either it can be thermosetting or it can be thermoplastic. So, thermoplastic means if you heat it will get melt and you can recycle, you can remold whatever shape you can want, you can do it. In case of thermosets or thermosetting, that means if you heat it will get harden, further heating it will get break. So, both the case rubbery material or elastomeric material are available. All materials have some elastic elongations. So, every metal have some kind of elongations. Elastic elongations equal to elongation of any material when that material is at its yield point. That means something it is giving the yield point, that is called elongation of material. Ceramic and metal, a small elastic elongation, that means is a very less elongation will be there, only 2%. Polyethylene elastic elongation is 50%. So, you can see the difference between some hard material have very less amount of elongation, whereas some soft material have more elongation. Stress strain diagram. So, this is the diagram will give a relation between stress and strain. So, if you this region which is called non-elastic region, elongation at break, if you further elongate it will get break, whereas this region is called elastic region, if you can elongate it will not get a break. So, up to this particular region in this diagram which is elastic region, you can apply strain, further apply strain or strength, that will get break. So, this is idealized stress strain curves for metals, conventional plastics and elastomers. You can see metals, it is a straight line almost. So, there is no much elongations, whereas conventional plastics have some kind of elongation in the curve, whereas elastomer have huge number of elongation against strain. If you apply strain, rubber material or elastomer material have more elongation than the conventional plastics than the metals. See, this is another diagram where you can see the molecular level. The diagram showing the random natural state of elastomer when under no stress and when stressed. Here you can see no stress, the molecule have what is the nature which is shown here. If we apply stress, the elongation takes place at the molecule level, will give the elastomeric property. A material may be elastomeric at room temperature, however rigid at low temperature. So, like a rubber material, you take it, you keep it room temperature, it looks like a elastomer. If you keep it freezer, it like a rigid material, you can't take it, or you just under low temperature you do it some any activity, it will get break. Why? There are amorphous polymers existing above their glass transition temperature. So, which we discussed in the previous lecture. Glass transition temperature, at particular temperature the material looks like a glassy, and some if above the material it will get rubbery nature. So, glassy nature, rubbery nature, particular temperature will separate these two nature of the material. Above their glass transition temperature, that the considerable segmental motion is possible. So, particular temperature you can do like a room temperature in the rubber, you can get the flexibility. If below the room temperature, like if keep it in freezer, you can't get the flexibility because of this peculiar property of glass transition temperature. At ambient temperature, rubbers are relatively soft and deformable. So, it is normal room temperature, rubber material are soft in nature, that is deformable, it can get elongations, whereas under low temperature it may not get the elastomeric property. Most elastomers are cross linked, that means elastomers are cross linked with either sulfur or some of the other material. Atoms between cross link can still move, uncoil and coil. So, because of cross linking, what will happen? It can move, the movement may be restricted, some of the case it may be coiled, or some cases it may be uncoiled based on the cross linking. The long polymer chain cross link during curing. Curing is the drying process, that particular process that may long polymer chain may undergo cross linking and account for the flexible nature of the material. So, while during the cross linking, the curing process will be decide whether how much flexible the material you need. Without a cross link, an elastomer may be elongated beyond elastic limit. With the cross link, max. The elongation is set safely within the elastic regions. So, this is if you do the cross linking, what will happen? The elasticity will restricted some of the cases, most of the cases. So, if you further increase the cross linking, the elasticity completely block, that is what mentioned here. If you beyond the elasticity limit, the cross linking may not allow. The cross link density, total number of cross link in the system, less elongation is desired, number of cross link can be increased. So, if you need the material should be less flexible or less elongation, you can increase keep on more number of cross linking. If you increase cross linking maximum, the flexibility will be less and that material may not be more flexible like elastomer. Natural rubber, rubber tree Hevia brasiliensis. Natural rubber is obtained by drying a latex rubber, which is a milk in which the butter fat component is suspended in water solutions. High temperature stability, cooking the crude natural rubber with the sulfur. You take natural rubber, crude rubber as such, you add sulfur and heat it, you will get more cross linking. The vulcanization creates cross linking between rubber molecules. So, each chain of polymeric chain, in between there is a cross linking with sulfur, that is called vulcanization. Natural rubber is highly elastomeric, elongation 1000% for vulcanized natural rubber. So, natural rubber which is have highly elongation property, that is elastomeric in nature. Compared to other elastomeric material, natural rubber shows high tensile strength, high tear strength, high resilience, resistance to wear. So, this is very important property like a high tear strength, resistant to wear strength and tensile strength. So, these three properties are very important which is present in the natural rubber, which does not present in the synthetic rubber. Some of the point may be, or most of the cases is all the 3 point may not be present in the synthetic rubber. That is the advantages over synthetic rubber to natural rubber. Natural rubber is still demand because of this peculiar property. Polymer repeating groups. The crude natural rubber was chiefly composed of cis polyisoprene, a polymer chain with a carbon-carbon double bond with a repeating unit. That means, I already discussed in the previous lecture the isomer whatever present in the polymer monomer, which is isoprene, which is cis in nature for natural polymer. So, cis means both component may present in the same side. Cis means that two pendant group like a hydrogen and methyl that are attached to the two carbons on the carbon-carbon double bond. So, two different carbon which is attached to CC double bond. The alternate configuration where two groups are located on the opposite sides of the carbon-carbon double bond is called trans. If the same side the methyl and hydrogen attached, which is called cis. If it is opposite side like a methyl group hydrogen attached to opposite side to the double bond, which is called trans. The presence of methyl group interfere the movement in polyisoprene. Polymer restricted bending and twisting motion, increased stiffness, higher strength and higher temperature stability. So, these are all the property based on the orientation of the methyl group. If it is cis, which have different properties, if it is attached in trans, which will give some other property like which is twisting motion, increased stiffness, higher strength and high temperature stability. So, this will be getting based on the orientation of the methyl group and hydrogen towards the CC double bond. You can see the structure here. So, this is a cis polyisoprene where the higher chain hydrocarbon both of them present on the same side. Alternatively, you can say methyl and hydrogen are present on the same side towards carbon-carbon double bond, and another isomer which is a trans where methyl group and hydrogen which is attached to the carbon-carbon double bond opposite. So, this is trans. Based on this cis and trans which is available on katta percha, which we discussed in the previous class, and cis is available for in our natural rubber. So, our natural rubber contains only cis isomer, whereas some other polymer rubber material gutta percha which have trans isomer. Whenever we required for some property like we discussed in the previous slides, though depend upon our requirement we can choose any one of the polymer or rubber material. Properties of cis and trans are quite different. Cis is highly elastomeric and sensitive to heat softening. So, that is the application. If you see this cis material, highly elastomeric, that means the flexibility which is very high and sensitive to heat. If you heat it, it will get softened. That is that means it is a thermoplastic in nature. While heating, it will get softened. Trans material is called gutta percha. You can see this is a trans material, the methyl group and hydrogen which is attached to opposite in nature. Much harder than cis isoprene unit for golf balls. So, making golf balls and all, that is used for trans isomer, which is much harder compared to cis one. During vulcanization process, sulfur will react with the carbon-carbon double bond. This is what happened here. If you are going for vulcanization, means CC double bond, one of the double bond will react and make a sulfur bond, and again another unit will make like a double bond to make a cross link between two polymeric chain. In between sulfur will be there. Synthetic polyisoprene or isoprene rubber. Disruption of supply of natural rubber during World War I and II increases need for elastomeric material, needs for the synthetic rubber. So, how synthetic rubber came into picture? Because World War I and II, all the natural material which is vanished. So, people may need of some kind of alternatives, then people went for some synthetic rubber. Synthetic polyisoprene made in early 1900 used for tires for lightweight vehicles. So, the same molecule produced in the laboratory synthesis like a polyisoprene, which is used for tires for lightweight vehicles, means it can lift easily. Combination of cis and trans molecular forms, mixture of properties. If you mix both two like a cis and trans, we have seen both two here. If you mix both two polymer together and make some product, that will give a mixture of property, like if you need some particular hardness, then you can go for trans isomer. You need more elongation, then you can go for cis isomer. If you put together, it will elongate as well as hard, both property will be present on the polymeric material. Ziegler-Natta catalyst system was developed in 1950s. So, inorganic people who worked Ziegler-Natta, two different scientists prepared this kind of polymer. It was found that 90% pure cis isoprene could be produced by this catalyst system. So, using Ziegler-Natta as an inorganic organometallic catalyst, using that you can prepare laboratory, make synthetic material with cis isoprene, you can produce in large scale with you no need to prepare for trans, because of this organocatalyst nature of the catalyst, only it will produce 90% of cis isomer rather than the trans isomer. However, the natural rubber is used more extensively because of its low cost. So, synthetic material which will be quite costly compared to natural one. Butadiene rubber, also known as BR, which is belongs to synthetic rubber. Repeating unit of both have a backbone of 4 carbon atoms, including carbon carbon double bond. Butadiene rubber CC double bond will present in the polymeric or rubberic material. Polybutadiene has just 2 hydrogens attached to the carbon carbon double bond. Absence of methyl group in polybutadiene results in poorer strength and stage strength than would polyisoprene. Resilient, it is about the same. Polybutadiene has poor resistance to solvent. So, this is the difference between the synthetic one, natural one. It have a poor strength wise is very poor, and tear resistance also very low, and which is resistant towards solvent. If you add solvent, it will be more stable than the natural one. Advantages of polybutadiene, which is a very low cost, improvement in low temperature, it can perform in low temperature, whereas our natural rubber cannot perform low temperature. The flexibility will reduce, it can get break, and it have a flexibility more than what natural rubber have. Compatibility with many other polymeric material, good adhesions to metals. So, towards metal, our natural rubber may not be suitable for in case of the synthetic polybutadiene, which is very suitable, and which also used for compatibility with other materials or element. Polybutadienes used better than the natural rubber. Butadiene monomer is added to the monomer of the other plastics. So, you can use one butadiene, you can use for any other 1 unit monomer, you can make a polymer which is called copolymer. So, copolymer is created. Butadiene monomer plus polystyrene will give styrene butadiene rubber, generally known as SBR, which can produce as a copolymer. Bulky styrene molecule add stiffness and intermolecular interference to butadiene, while butadiene add flexibility and toughness to the styrene. So, mixing two things will give, we can improve two different property, like one can take care the toughness and another one can take care the flexibility. So, that is the beauty of making copolymer. You can whatever material you need, which particular properties, you can choose the monomer and you can do the copolymerization, you will get the particular polymer which have peculiar properties. So, example shown here. So, this is butadiene react with the styrene, undergo polymerization, will produce styrene butadiene rubber SBR. So, you can see here this is styrene unit, this is butadiene unit. So, which can give more flexibility, this will give more toughness and strength. And butadiene, simply the polymer butadiene rubber, generally known as BR, the butadiene undergo polymerization will produce polybutadiene, which have a double bond in the monomeric unit. So, if you, it may be two types, it can be 1,4 polybutadiene cis, the hydrogens are both are same sides, whereas the hydrogens are opposite side, which is trans, 1,4 polybutadiene. So, depend upon polybutadiene from obtained from butadiene, it can undergo two types, either cis or trans. Based on your requirement, you can go for either cis or trans. Another class is thermoplastic elastomer. Thermoplastic, which is while heating it will get melt. These materials are not cross linked, have some distinct processing advantages over traditional thermoset elastomers and physical properties of vulcanized elastomers. So, which is have some different properties compared to vulcanized elastomers. It does not have more cross linking. That is why if you heat it will easily melt or it will easily get softened. Thermoplastic elastomers are able to be molded like a thermoplastic, injection molding, extrusion, etc. These are all types of molding. Whatever way you can mold or whatever shape you want, based on that you can make this thermoplastic material. Thermoplastic elastomers are more temperature sensitive. That means, if you heat it further, it will get soften, further heating it will get melt. So, another class which is a very high strength polymeric material, which is silicones or polysiloxanes. Silicones or polysiloxanes are inorganic organic polymers. Silicon belongs to inorganic metal, and this methyl and oxygen and all comes under organic. So, it is generally organic inorganic hybrid material with the chemical formula. This is R2SiO n times, where R is organic groups such as methyl, ethyl and phenyl, etc. The material consists of an inorganic silicon oxygen backbone. This SiO will keep on repeat the entire polymer chain, which will give backbone of the strength of the polymer, where this methyl, instead of methyl you can choose ethyl, propyl, butyl, benzyl, whatever may be, to strengthen the strain. With organic side groups attached to the silicon atoms with the 4 coordinate. In some cases, organic side groups can be used to link 2 or more of this SiO backbone together. By varying the SiO chain length, side groups and cross linking, silicones can be synthesized with wide variety of properties and compositions. So, you can change the side groups like silicon attached to either methyl, ethyl, butyl, whatever may be. If you change the side group, organic group, it will give different properties. So, based on the property you can prepare more number of elastomeric materials. They can vary in consistently from liquid to gel. If you keep on change the R group, alkyl groups, organic groups, it will vary from liquid to gel. That means, slowly it will get solid state to rubber to hard plastics. The most common type is linear polydimethyl siloxanes or PDMS. We have seen this is a linear polydimethyl siloxanes. Silicone or polysiloxanes, service temperature to about 260 degrees Celsius, we can use up to this temperature. Good chemical resistance, low water absorptions, because of silicon oxygen strong bond, it is almost act as a inert material. It is resistant towards chemicals and it will not absorb water. So, most of the case it can be used as a raincoat and all these other water repellent properties. Good electrical properties and available in flame retardant grade. So, it cannot be flammable. So, if you want to make any flame retardant, that you can use for silicone, polysilicones or polysiloxanes. In the plumbing and automotive fields, silicone grease is often used as a lubricant. So, this is used to one of the very important application is used as a lubricant. In plumbing, the grease is typically applied to O-rings, the faucets and valves. So, wherever you repaired the flexibility, there you can apply this kind of lubricant. The lubricant nothing but silicones or polysiloxanes. In the automotive field, silicones grease is typically used as a lubricant for brake components. Since it is stable at high temperature, it is not water soluble. So, this is because of two important properties, it can be used for high temperature industrial works. So, processing of elastomer, elastomer can be processed like this. So, you can kept in between the rolling bank or you can go for roll mill. So, common machines used for rubber compounding, these two machines we can make, either you can put it the rubber sheet and you can roll it, you will get a sheet, dried thick sheet. Similarly, you can use these kind of machines to get processing of elastomers. Applications of elastomer, it have a very good applications. Bearings structural joints that are installed between structures and its foundations. So, this is foundation, this is a structure, in between you can keep this kind of elastomeric material. The bearing is very stiff and strong in the vertical direction, these directions, but flexible in the horizontal directions. So, the elastomeric material flexible in the horizontal direction and it is very stiff in the vertical direction. It never undergo elongation like this, it will undergo only elongation like a horizontal manner. So, in case of building construction of building, base isolated and fixed base buildings. This is fixed base buildings, this is isolated building. A base is isolated structure is supported by a series of bearing pads which are placed between the buildings and the building's foundations. You can keep some foundations bearing base. As a result of an earthquake, if some earthquake happen, the ground beneath each building begins to move. Each building responds with a movement which tends towards the right. The building's displacement in the direction opposite the ground motion is actually due to inertia. So, ground motion like this, the building motion will be opposite to the ground motions. What will happen if we keep some polymeric material elastomer, the building will move like this and it can get back to its original position, whereas if there is no support of such a material, it does not have any flexibility, it may possibility to get fell down. In addition to displacing towards the right, the unisolated building is also shown to be changing its shape from a rectangle to parallelogram, deforming. So, rectangle to parallel means this is not in the forming, it is getting deforming, whereas which is in the same forming positions. The primary cause of earthquake damage to buildings is the deformations which the building undergoes as a result of the inertial force acting upon it. So, once the building is deformed, the entire damage may happen, whereas here if you keep this kind of elastomeric material in the bottom, it may not undergo deformation. So, further damage can be avoided. The base isolated building retains its original rectangular shape, this is one, and it is elastomeric bearings supporting the building that are deformed. So, whatever without supporting that building is getting deformed. It implies the inertial force acting on the base isolated building have been reduced. This isolated building, whatever force acting from the earth which is reduced here compared to this one. So, this building getting damaged, this may not get damaged like this. Basic structure of rubber bearings here consist of thin rubber sheets bonded onto thin steel plates and combined with an energy dissipation mechanisms. Elastomeric bearings, the rubber sheets are vulcanized and bonded to the thin steel plates under pressure and heat. It is designed in such a way that the bearing is very stiff and strong in vertical directions. That means, each polymeric material kept with vulcanized product. So, which is elongated in the horizontal direction, the vertical direction may be restricted using more vulcanizations, but the flexible in horizontal direction. So, it can be flexible with the horizontal directions. Thick mounting steel plates are bonded to the bottom and the top surface, allowing the isolator to be firmly connected to the foundation below and the superstructure above. So, foundation means pillar. If you make a pillar in the below and you can keep the polymeric material or elastomer and make the structure in the above. So, this material, whatever polymeric rubber material kept here, which is having more cross linking. So, what will happen, this material may not elongate in the vertical positions, it will elongate and takes place only in the horizontal position. Based on this, it can work or it can save the buildings. Processing flow chart for seismic rubber bearings. So, raw material which can be mixing and preparation of rubber sheets and metal preparations, adhesive applications, you can combine together, produce assembly of metal and rubber in a mold, compression moldings, inspections, finished products. This product can be used for those applications. So, in this lecture we have seen what is elastomer and elastomeric properties and rubberic properties, how elastomeric property can be restricted or enhanced, what are the types of monomer unit or polymeric unit present in the elastomer, types like thermosettings and thermoplastics, and we will take cis isomer and trans isomer, everything have different applications, all these things we studied. And introductions about elastomers we had studied, elastomeric material also known as rubberic material also we studied in details, synthetic polyisoprenes which is similar to natural polyisoprene which have some drawbacks and advantages that we studied, silicones and siloxanes which is organic inorganic hybrid elastomeric material also we studied, butadiene rubber, butadiene and styrene copolymer also we studied, thermoelastic butadiene that we studied in detail. Questions of today lecture is what is elastomers, give examples of elastomeric material, how to do synthetic polyisoprenes and how to make silicones and siloxanes elastomer, what is butadiene rubber, give examples, what is thermoelastic butadiene, give 2 examples. Within this I conclude this lecture. Thank you.